So if you look back in memset takes a pointer to, and then a value to initialize it to, and then how big is the thing, or how many bytes, right? First num bytes. So we would go back over here. This pointer, right? Elements to 0, and there's num elements times size bytes for the space, and then we would return elements. I mean, that's all calloc does. The memset just goes through that section of memory and sets everything to 0. We could do it as an array, but you can't really like index the void pointer because it's doesn't know how big the elements are. And I could do some fun casting to probably make it work, assuming that a char was 1 byte big, and that would definitely do it. But just using memset's a bit safer. This is calloc. Any other questions? Yes. We'll get to that. What do you think about malloc or calloc? So like when you make a call to malloc, let's say we did something like I want to malloc, 4 bytes worth of space. What malloc is going to do is it's going to go over here and create 4 bytes worth of space. It might make the first one at 100, 101, 102, 103. Right? So it goes and it creates this space over here. And then malloc gives you back a pointer to where this memory begins at. So where does this memory begin at? 100, right? So if I had something like star p is equal to here, p is equal to malloc, p's value is just equal to 100. That's where it's at. And so when you're working with arrays are just sections of memory that you know the beginning of. And so one thing that you haven't seen is when you do something like this, like p at I, which is totally valid, what this really secretly is it's p plus I dereferenced. Go I elements past p and then dereference it. So let's just say there's like A, B, C, D here. If I do p at 2, right, that's equal to p plus 2 dereferenced. So what's the value of p? 100. So what's 100 plus 2? 2. What's there? C. And that would give you C. Both of these expressions give you C. The brackets are a secret dereference that you didn't know about. They just like go I elements past where that pointer starts, and then take the value that's there. Does that make sense? Or if we did something like, p at 3, star p plus 3, first, right? P's value is still 100, so that's going to be 103. Right? So the full expression would be 103, and then the value that's there would be d. The full expression over here would be 102, whose value is equal to c. That's it. One other thing I should note is that star and ampersand, they're inverses of each other, right? Ampersand means get the address of. Star means go there. So like if you do like the star of the address of p, like give me p's address, then go to that address. So that's just equivalent to p. Or if you do p, if you do star p and the address of, right, that means go to where p is pointing to and then get its address. This is also equivalent to p. So sometimes you might do something like this, Scanf, right, into something like, %d into the address of the array at I, right, if you're trying to read an array. Well, we said that AR at I is just, AR bracket I is AR plus I, dereference ampersand. We said ampersand and star are inverses of each other. They cancel out, so we could write this scanf statement as just scanf %p AR plus I. Yeah. Yeah, this says, go to the ith element of the array. and then go and whatever scanf feeds in, go put it into this address. Any questions there? Okay. And then so here's an example of us making a random matrix, and we're going to return a pointer back to that space that we created, and I'll go do a drawing afterwards. So the first thing that we do is when we're dynamically creating space, it's just kind of like in Python where you have like an array of arrays. Here we're also going to have an array of arrays. We're going to have an array of integer pointers, and each of these integer pointers will then point to an array of ints. So first thing that I do is I make space for the rows or the integer pointers here. And again, notice this, type pass is the type of the thing on the left. Calloc, how many rows, size of, star pointer, or star of whatever the variable's name is over here, so star mat. Then we go through each one of the rows, actually making space for the elements. So mat at row is equal to another calloc calloc. And again, notice that I dereferenced the expression I have on the left-hand side of the equal sign. So star mat row. And then I go through and I fill in the values. Mat at row equals some random integer. And notice that this indexing looks exactly the same as indexing a multi-dimensional array that you've declared statically, which is kind of nice. But behind the scenes, it's doing something a little bit different than with the static arrays. Any questions on this piece of code here? So that first call to malloc when we're making the pointers is over here we have mat, and let's say we're trying to make a 3x4. So here we have mat, and it's going to point to a list of pointers. And that first call to malloc would make space for 3 pointers. Each of these guys type over here is integer pointer. And if mat is going to point to integer pointers, what's mat's type need to be? Integer pointer, right? You need to be one more star than the thing that you try to point to. You want to point to an integer, you need to be an integer pointer. You want to be a character, you want to point to a character, you need to be a character pointer. If you want to point to integer pointers, we need to be an integer pointer. This guy might be at location, say, like 100, 101, 102. Then we go through each one of the rows and we allocate space for the elements that are going to be in there. That second call to malloc inside the for loop. So first we create space for 4 things. This guy might be at 400, 401, 402, 403. And then malloc's going to give us back or calloc is going to give us back a value. What value is it going to give us back? 400, right? It's going to give you back the address of where the array begins at in memory. So we're going to put our 400 over here because we said mat at row, mat at the index that we're on, is equal to whatever calloc returns. We're going to store the address of where this array lives at in memory. So now pointing over here. Then we go to the next iteration and make space for 4 more things. This guy might be at something like 700, 701, 702, 703. And so what's calloc going to return? 100, right? Where this array begins at in memory. And we store that value, and now we point here. And then finally create our last array of 4 elements. This might be at address 6, 7, 8, and 9. And so calloc is going to return 9. So then we would go fill it in, right? We do something like mat at ij. Well, if you want to write this expression without brackets, which I'm not going to make you do, but it would be mat plus I, dereference, plus j, dereference. And so if we're doing something like this, like mat at 1, 2 is equal to 77, what we would do is mat, what value does mat have in it? What's the value in mat based on my example? 100, right? Mat's equal to 100 because it's pointing at address 100. So if we're doing this expression right here, what the compiler is going to do is going to take mat, right, which is 100. Then we're going to add I to it, which is 1. And then we're going to dereference it. So what's 100 plus 1? 101, and then we dereference it to get the value that's at that location. So what do we get now? This expression turns into 700. Then we're going to add 2 to this, and then dereference again. So 700 plus 2 is 702, and we're going to go to that location in memory and change its value to 77. So when you have these arrays of arrays, these dynamically allocated multidimensional arrays, this is how they're structured. It's an array of arrays. Any questions here? Yes? So it's the index is going to be how far it actually moves. It's going to be based on the size of the pointer. So like if you say like if you have an integer pointer and you do an integer pointer plus 5, a character pointer plus 5, integer pointer plus 5 is going to move a little bit farther than the character one internally because an integer is larger than a character. But conceptually, both are doing the same things. The first one's saying move 5 integers past this location. The other one's saying move 5 characters past the location. The type, but you probably shouldn't need to worry about that too much right now. Any other questions? Okay. So we also have this exact same example over here again, but instead of returning the value via a return statement, I'm going to return the value by setting an out parameter. And if you remember from Wednesday, if you want to change a variable of type x, right, we need to return at least, or our function needs to accept at least a pointer to type x, right? So on line 50, I want to be able to change the double pointer. So my function has to accept a triple pointer, which is why we have the triple pointer over here. So you can say here, it says, I say, hey, go to wherever that location is that you want me to put the values at. I'm going to make space for numRows pointers there. Or actually, I'm going to go make space for numRows pointers. I'm going to set you to go point to that location that I just made. Then we go through and we make the space for the elements. And then we go through and we fill them in. Notice that when we're doing this, we need to actually go to that location in memory first and then index past it on line 55. But the brackets have higher precedence than the star operator. So we need to make sure that we enclose star mat into in parentheses so that we do the dereference first before we do the indexing. And I'll give you a drawing first to show you why that's important. And then the same thing is happening down here. I need to dereference mat first before I can do the indexing so they actually end up in the correct location in memory.
First row, like, you have to do it.
You'd have to do it like element by element, but you could use things like, if you wanted an exact copy, you could use things like memcopy to say copy over all the things. Or you could write your own function to do a copy, and you could just call it everywhere you needed it. So with this second version, here might be what we did at the beginning. But now what I have is I have a pointer to mat, right? This is the triple pointer. He's going to go point over where? To mat. And let's say mat happens to be at address 63, right? Just making a location for where mat happens to live at. So we pass in the address of mat so that we can now modify it inside the function. So if we had done the expression earlier, like mat at I, and then dereference, and we did the dereference second, again, if we rewrite out this expression without the brackets, It's going to be mat plus I, dereferenced, dereferenced. And hopefully you can start seeing why that's probably not going to make much sense. Or I should say PMAT here. So let's say I happens to have the value 2. Right? So what's the value of PMAT? So 63 plus 2, right? Which is going to be, so now we're going to go to address 65 and get the value that's in there. Based on our drawing, what's at address 65? I have no idea. So I went to some random garbage location in memory, and I'm trying to go like dereference whatever value happens to be there to go access it. And that's probably going to cause a lot of problems to me and give me a segmentation fault. Because there might even not be a pointer there. And if there is a pointer there, then you probably even got extra unlucky and you're just going right into some random other location in memory you didn't intend to. Whereas if we do it the other way around, star PMAT at I, again, this is going to be rewritten without brackets. It's going to be star PMAT plus I dereferenced. So again, what's PMAT? PMAT's still 63, right? So then we do star PMAT. Go to address 63. Oh, what's at address 63? It's mat, right? So this expression evaluates to be 100, and then we'd have 100 plus the 2, right? We go to location 102, and we're good. We can get the, if we index the 6 here, if we go to 102 and then we dereference to get the value that's there, we get the 6, which is where this array begins at in memory. Does that make sense? This is like a gotcha that gets a lot of people when they're doing things like read lines, because they forget they need to dereference the pointer first before they can do their indexing, so they end up in the right location in memory. Here? Here? Yeah, I mean, like anywhere where you're just adding the integer to a pointer, it's pointer arithmetic, right? And the brackets are a secret form of pointer arithmetic followed by a dereference. Like ninjas, they're really secret. They're cool like ninjas. We probably want to prefer to use the brackets, make our lives easier than to keep using the addition than the dereference. So that's really what's happening. You need to pay attention to that to end up in the right location in memory. Any questions here? Yeah. On this one right here. Yeah. You guys remember we said that bracket I means plus the thing on the left, then dereference. Right? We said that down here, like array at I is equal to array plus I dereferenced. See what's happening? So here when we do the PMAT bracket I, that's PMAT plus I dereferenced. Then we still have this dereference over here, so it's going to dereference it twice. But we need to dereference PMAT first, then move I past that location, and then dereference again to get the correct value. So once you create space, it's really important that you make sure that you destroy that space when you're done with it. Because if you don't destroy that space when you're done with it, you are going to get a memory leak, and that memory won't be reclaimable. So here's an example of destroying the matrix. When you destroy it, you have to go through like the reverse order of the declaration. Remember, first we made the rows, and then we made the elements per the row, or for each row. So now we're going to go through and we're going to destroy the elements in the row, and then we're going to free all the rows. The reason for that is because if we freed all the rows first, we deleted all those pointers, we would no longer have any pointers to get to the other locations to be able to delete them. So what's happening here is first we go through and we would delete this, delete this, delete this. Then we would go through and we would delete this. Notice after we delete this, what value is still held in mat? 100, it's still pointing there to this deleted space. So one thing that I recommend is like after you free something, take your pointer and set it to null afterwards. This will help you catch mistakes a lot easier than if you just leave it to be 100, because the 100's undefined behavior is much harder to catch. So after you free the pointer, make sure that you set it to null. But why would this kind of be useless to do? Here. Well, I'm not returning it, I agree, right? But some of the reason is, it's not quite the reason I was looking for. Well, I mean, mat, yes, is created on the stack, but again, not what I'm looking for. I mean, I deleted it first, right? So that shouldn't be a problem. Yeah, when we called this function, right, we passed a copy of the pointer. So who did I change, the original or the copy? Change the copy, right? So the original still would be pointing to location 100 in our example. So if we wanted to be able to change mat, our function would have to accept a triple pointer. So if we go to here, we might have something like void destroy matrix and set to null. Integer pointer mat. Integer numRows. And so most of our code's going to be the same, except we're now going to have to throw in some extra stars there. So copy and paste this. But now I want to free mat at I, and since it's a triple pointer, what do I need to do? Dereference it first, but I need to dereference it first. So parentheses, and then star over here, and then afterwards star mat equals null. And this will set us to point, actually change the original to point to null. Oh yeah, sure, why not? Probably even smarter. We could say like destroy matrix, star mat, numRows, and then we set it equal to null. So here's an example of realloc. When you realloc, you specify the pointer that you want to resize, and then you say, well, what do you want your new size to be? Realloc can only be used to resize things that have been created by malloc, calloc, or realloc. So you cannot resize anything that's just on the stack. It's not going to work. So for my insert, I say what value, what position into my array. And because I need to modify the array itself by resizing it, I have to take another pointer to it to be able to change it. And I'm also taking in length because I want to be able to modify that. So I increase length by 1, and then I actually resize down here. So my new array has now been made 1 larger. And when you add space, the space gets added to the end of the array. Then I need to go through, I need to take all the elements to the right of the position that I want to insert. I need to shuffle them all over, move them all over to the side. So I go and I move them all over, and then I go and I put in the value at the position that I wanted. Questions on this one? Yeah. Oh, yeah. Sketch. Didn't have time to double check these ones yet. Any other questions? Yeah. The question is, when you call free, how does it know how big the thing is? Because regardless of how much space you allocated with that one call to malloc, it will release all the space. Malloc keeps track, or calloc keeps track of like how big that space is. Correct. I don't know. That's just how it is because it doesn't give you back the size. I mean, it assumes that, if you ask for 30 things, like, that you asked for 30 things. Yeah. So the question is, why do I shuffle the elements over to the right? Let's assume that here's my current array. It has just like A, B, C, D, and E in it. And let's say that we wanted to insert the value D at position 2. So the first step that we need to do is we need to make space for that new element. So we resize A, B, C, D, E. Then we have this blank space over here now. Right? And now I need to move each element over into the right. So take this guy, move him here. So then after the E's been moved over, move the D over, and after the D has been moved over, move the C over. This is going to cause the array to look like A, B, C, C, D, E. And now at position 2, I wanted to put the Z, so I go to position 2, and I replace that with the Z. Does that make sense? That's why the elements need to move over to the right, because the new space that I've created is on the right, not on the left. I mean, well, Z is going to go wherever I specified. So if you want to do an append function, right, you just resize to be one bigger than what you are, and you go put it in at the end. If I wanted to do an insert, put it somewhere else besides just the end. Any other questions? Realloc can also be used to do a free, and can also behave like malloc. So if you realloc a null pointer, realloc will behave like malloc, and then it'll just make the space. Right? This is different than reallocating an uninitialized pointer. If you try to realloc an uninitialized pointer, you're probably going to get a segmentation fault. If you realloc down to 0 bytes, realloc will behave like free and it will delete all the space that's there. So realloc is actually like pretty powerful. So here is a function that will read a string of any length from the input. And because we don't know how big the string is going to be, we need to make space for it as we go along, one character at a time as we bring it in. And our string here is we're going to keep reading non-white space characters until we reach the first white space character. So here I start my string as null. Again, this is really, really important so that when I realloc down here on line 100, it works. If I don't do this, that's undefined behavior. Because now string has some unknown value and I tried to go realloc some garbage location. It'll cause an error. I've also read in 0 characters first. So what I'm going to do is I'm going to make space for that new character, len++. Then we are going to realloc, stir, I want to resize it to be that new size because I've already added the +1. I need to store the result back in stir. It's really important when you do these reallocs that you make sure to store the return value back into the pointer that you've resized. This is because normally if realloc is able to find space next to where your array is already at, it'll just use that space and it won't move any of the elements. But sometimes when you do a realloc to get larger, there won't be enough space nearby you because it's already in use to be able to do that. So what realloc will do is it's going to go find some other location of memory, create enough space that's reserve that space for your program that's big enough, take all the elements that you originally had, copy them over, and then give you a pointer to that new space. So if you don't do this assignment and realloc had to move your memory location, I should say realloc will then free the old location, you'll be pointing to some deallocated space of memory and get an error when you try to dereference it. So make sure that you reassign. It will destroy the old space, yes. So make sure that you do this reassignment, and then we read in the first non-white space character into this space that we just made. Any questions on lines 99 through 101? So then we keep going. True. We make space for that next character. Reallocate our array to make it a little bit larger to fit it. Read in that next character. But this character, the difference between lines 100 and or 101 and 109 is that here we're only going to read a non-white space character, so we skip all the leading white space, just like the %s string will do. Here we're okay with reading white space because I need to be able to check it in 1 second. So if that character that we just read in is white space, I'm going to replace it with the null character. And again, strings are just arrays that end with the null character. So it's really important that I put that null character in there, otherwise it's not a string. Does that make sense? And then I'm just going to return string. The space was created on the stack, and I'm going to assume later on that whoever called this function will eventually delete that space when they're done with it. If you realloc to be smaller, let's say you go from 10 down to 4, you'll keep the first 4 elements of your array. You'll lose the last 6. No, so if you realloc to be down smaller, those values are not considered to be a part of your program anymore. So they're freed up, and so that space can be reused in the future. There's no guarantees on whether like malloc will or like realloc will like zero out that memory. It probably won't. So the values would still be there, but you just don't have a way to access them anymore. You don't have a valid pointer to that location in memory. You mean, can you say like, I want an integer pointer p equals 5,000?
Yeah, something.
Sure. It's probably not going to work when you dereference it, but sure, you can do it. Yeah. Yeah, so those elements that, so if you realloc to say like from 10 down to 4, and then you realloc back to size 10, those elements that were there, the last 6, they're not guaranteed to be there, and the values that are in those spots are uninitialized. They may or may not, and it's really like compiler dependent behavior, and you shouldn't trust it to be there because it's not going to work all the time. Any other questions? Yeah. So there's a question, is there a way to figure out how much space that pointer is pointing to? No. You got to keep track of it with another variable. Or here, since we're doing a string, it's okay because strings end with a null character, and you know to look for that null character. But for like other arrays, you have to like also give back a size. This is why something like insert also took a pointer to the length so that it could increase it by 1. Any other questions? So I'll finish that one and make that example later. I started writing, wherever it's at. I started writing split, you know, everybody's favorite Python function, but I didn't have quite time to finish it this morning. But split is kind of complicated if you want to try it out. Because you have to go parse the string and then split on the character, then you have to keep making new arrays, and you don't know how big the arrays are going to end up being. Fun. So do you guys have any questions or confusions still surrounding pointers? So when you realloc space to become larger, the space is going to be at the end of the array. So if I realloc from 4 to 10, I'll get 6 more spaces at the end. And there's no way of getting space at the beginning. If you wanted to like realloc space at the beginning, you realloc space at the end, you have to move everybody over. Make that happen. Any other questions? Okay, let's talk about a very quick topic. This is in the ECS30 slides. And we're going to talk about command line parameters, which should be pretty easy to understand. So if you guys remember when we were talking about the command line, or when we were working on the command line a little bit ago with commands like ls and echo and pwd and whatnot, they would all take in, you would type in their arguments like ls some directory or cd into some directory. It wasn't like ls. And ls is like, please tell me which directory you would like to read from. And you typed it in, right? Like the programs that you wrote for the very first one. So if you want to be able to accept command line arguments, you have to add two parameters to main. The first is called argc, it's an integer, and the second is argb. The names don't matter, the types are what's important. So you can call argc whatever you want it to, and argv to be whatever it's want. These are the traditional names they're given. Argc contains the number of command line arguments that you were passed, and argv actually contains the command line arguments. But argv is a array of strings. And the reason that it's an array of strings is because a string can represent any type of input you want, right? It can represent characters, like Matthew, some name. But it could also represent just a number like 56.32. One thing to point out is that argv0 is always going to be the name of the command that was used to run your program. So here's a little example of getting input on the command line. So here we have argc, argv, and then we go through each one of our arguments and we just print it out. So if I ran my program with hello 24 hi some number, arg0 is the name of the program, a.out, arg1 is hello, arg2 is 24, arg3 is hi, and arg4 is 735.59. Remember, these are all strings. So even this guy right here, he's a string, not the actual numeric value. You get the path to the file, right? So if someone said like, /user/home/bob.txt, right? That would be the string that you would get. I should still have like 1 minute left, I think, right?
So if I just pass something,
I have 2 minutes left. Just keep sitting there.
So if I pass something that was in my directory that I passed in, like let's say I was executing a file, there was like a test file that I wanted to throw in. Would it be ./test file, or would it be just
so you can say test file, that would be a relative path, or ./test file, that would also be a relative path. So sometimes, yeah.
So when you pass a argument to a file that's in the same folder as a working directory, is that expandable to the full?
So the question is, if you specify a path to a file on the command line, will it be expanded? No. So if you say like, hello.text, what you really get is hello.text. And if you later did a call to fopen, it's going to say fopen hello.text and interpret it as a regular path, or just that relative path. So sometimes the values that you get in, you don't want them to be strings. You want them to be numbers. And the function that's really helpful here is Sscanf. So Sscanf is exactly like scanf, except the first parameter is the string you want to read from. So you say some string, the format of what this string is supposed to be, and then what variables do you want to read it into. So if I had the string, 3 space 5, and I did it into %d, x and y, it's going to convert it in, right? Or 34.27, this will convert it into that double. Or if we wanted to read argv1 and convert it into an integer, we could do it with Sscanf. That's the tool that you want. I will see you guys on Monday or Wednesday, or in whatever we're going to next discussion.